Hi, I'm presenting mechanisms for no-regret agent beyond the common prior. My name is Modibo Camara. I'm an economics PhD student at Northwestern University, and this is joint work with Jason Hartline and Aleck Johnsen. A high-level question in algorithmic game theory is, can we replace prior knowledge assumptions that are common in our models with models of statistical learning? Much prior work suggests the answer is yes. So for example, no-regret assumptions borrowed from the theory of online learning have proven useful in a variety of game theoretic problems and can meaningfully discipline the agent's behavior. On the other hand, we have seen that no-regret algorithms in these settings can behave in bizarre ways. We will see some additional examples of this later in the talk. So one can ask whether models of learning can be adapted to handle strategic interactions more appropriately. We're going to be exploring these questions in this talk in the context of a class of problems that we will call single agent mechanisms. More formally, these problems are stackable games of incomplete information. And they include problems like contract design, Bayesian persuasion, delegation, and a variety of other settings that are of interest to economists. In these problems, we have a principle that decides on a policy, for example, whether to allow parking or to ban parking in a certain area. An agent that responds to that policy, for example, whether to take the car or to take a taxi. And a payoff that depends on some hidden state of nature, for example, whether the policeman is on duty or at the donut shop. These models usually require a common prior belief about the state in order to be solved. So a common prior might specify, for example, that the principal and agent agree that there's a 40% chance that the policeman is at a donut shop. Now, what we want to do is we want to relax the common prior assumption and replace it with adversarial online learning. By adversarial, of course, we mean that we're not going to make any assumptions on the sequence of states. Here we have the principal and the agent interacting repeatedly, followed by nature choosing some state, which is then observed by both the principal and the agent before moving on to the next round. We are going to be designing low regret mechanisms on behalf of the principal using permissive assumptions on the agent's behavior. These assumptions are going to be a refinement of no regret assumptions that we call counterfactual calibration. Now, counterfactual calibration roughly requires the agent to fully and consistently exploit her information, where information is basically something that is revealed through the agent's behavior. In the presence of information, what we'll find is that no regret assumptions are not going to be sufficiently restrictive and are going to allow a lot of pathological kinds of behaviors that make the principal's mechanism design problem infeasible. To illustrate this, we can turn to an analogy. So consider the classic fable of the tortoise and the hare. We might consider a statement that says, for example, a tortoise is going to finish the 1 kilometer race in 1 hour, right? The tortoise finds this feasible, let's suppose, but challenging. So the tortoise has to go in a straight line as fast as it can. That's how we can think about a statement that says an uninformed agent satisfies no regret, right? We can think about this as more or less implying that the agent has to behave in an empirical way. However, once we upgrade the tortoise to the hare, right, a quicker animal, or the uninformed agent to the informed agent, things become more difficult. So if we ask a hare to travel 1 kilometer in 1 hour, of course, this is very easy to satisfy, and the hare can, go in circles, start and stop, what have you, engage in all kinds of frivolous behaviors and still meet the requirement. Likewise, an informed agent can satisfy no regret while engaging in all kinds of pathological behaviors that make the principal's problem difficult. Now, the natural solution to the analogy is to calibrate the benchmark to the speed of the animal, right? So if we ask the hare to travel 1 kilometer in 2 minutes, then the hare has to go straight ahead as quick as it can. Similarly, what we want to do, the idea behind counterfactual calibration, is to have the informed agent satisfy no regret conditioned on her information, where information, again, is going to be revealed through the agent's behavior. Now, we'll get more into this later in the talk. For now, let me outline what we're going to be talking about. So first, I'm going to introduce a simple contract design example, okay? In the paper, we have a more general setup, but this example is going to be sufficient to sort of illustrate the key ideas that arise in the paper. We're going to talk about the mechanism and the main results, the regret bounds for that example. And then we're going to spend the rest of the talk trying to understand and motivate counterfactual calibration. So one example is this. We have an agent that faces a task of unknown difficulty. The difficulty is either easy or hard. The agent can either work or shirk at the task, and the outcome is either success or failure. In particular, it's success if and only if the agent works and the task is easy. If the task is hard and the agent works, there's still a failure. The principal, who we can think of as maybe as an employer, right, and the agent is an employee, the principal wants to incentivize the agent using a wage contract that specifies, given some observed outcome, success or failure, how much is the agent going to be paid. The agent's utility are her wages, given as specified by the contract for the realized outcome, minus some cost of effort C times an indicator for whether she works or not. The principal's profit is going to be some revenue R times an indicator for whether there's a successful outcome minus the wages paid to the agent. Now, these kinds of models are usually solved using a common prior assumption. A common prior says that the probability that the task is easy, we'll call that probability P, is commonly known to both the principal and the agent. Now, supposing that the parameter values are sort of in a are set so that the problem is non-trivial, and the agent is maximizing expected utility, the optimal contract for the principal is going to incentivize the agent to work by making her exactly indifferent between working and shirking. Specifically, it's going to pay her conditional on success, her cost of effort divided by the probability that the task is easy, and after failure, pay her nothing. Now, the common prior can be used generally to obtain all kinds of elegant, insightful solutions about various kinds of problems, but it is a clearly problematic assumption in many settings. So, of course, naturally, we can ask, what if the principal does not know the probability P, right? Then the contract described or solved under the common prior assumption cannot be sort of immediately applied in the real world because it does depend on this prior knowledge. One thing that we could do is we could substitute the principal's beliefs about the task for this probability P, but then we run into the question of why should the agent share the principal's beliefs, right? Is the common prior assumption really realistic in that setting? Now, of course, we're not the first people to say that the common prior assumption is problematic in some cases. And there's, in fact, a large literature in economics and in computer science that aims to relax the common prior assumption. A lot of the work, particularly in economics, but also in computer science, has proceeded by removing the common prior assumption without a replacement. Now, this is very successful in some settings like auction design, but very unsuccessful or limited in its ability to be successful in problems like the contract design example I showed you, or other problems like Bayesian persuasion, where the distribution of the state really is vital to the solution. Now, working algorithm game theory has relaxed the common prior and replaced it with models of learning, models of batch learning or stochastic online learning, as well as, to some degree, models of adversarial online learning, where, again, we're not making any kinds of distributional assumptions. Our paper is contributing to this, replacing the common prior with adversarial online learning. Similarly, prior work can relax the the common prior on the principal side, relax knowledge on the agent side, or relax knowledge on both the principal and the agent side. And the latter is what we're doing. So we're going to be relaxing both the principal and the agent's knowledge and thinking about them both as potentially learning about the states. Okay, so let's introduce our sort of framework of adversarial online learning applied to mechanism design. So we think about a sequence of tasks 1 through T. So again, this is for a running example. Task T, we're basically going to replicate the one-shot game that I just described to you. The principal chooses some contract WT, the agent chooses some action AT, depending on, after having observed the contract. Nature chooses some difficulty DT. The outcome OT depends on the action and the difficulty, and the agent receives some wage that, again, will be whatever the contract specifies for the realized outcome. The history of task difficulties, past contracts, and past outcomes is mutually observed by the principal and the agent. The agent's learning algorithm is going to map the history to some action AT. And the principal's mechanism is going to map the history to some contract WT. Our goal is to design a mechanism for the principal that obtains low regret for the principal, right? Of course, we don't have here any distributional assumption, right? So the sequence of difficulties is arbitrary. So we can't just maximize expected utility. Instead, we'll turn to no regret as a criterion for the principal. So the principal's regret from mechanism M is as follows. So on the right-hand side, we have the average profit under the mechanism M. So if the principal follows mechanism M, this is the average profit. If the principal follows a fixed contract W, the left-hand side describes the profit. So fixed contract says you have a contract W and you're going to play it in every period, regardless of the history. You notice that we have a maximum over W. So we're going to say, okay, on the left-hand side, we have the average profit that the principal would have obtained from the fixed contract that is best in hindsight, given the realized sequence of difficulties. And the difference between this best in hindsight payoff and the payoff that the principal actually obtained is the principal's regret. More precisely, WT here denotes the contract specified by mechanism M for task T. AT describes the agent's action if the principal follows mechanism M, and ATW describes the agent's action if the principal follows the fixed contract W. Now notice here that AT and ATW might differ because the principal's choice of mechanism will affect the history of contracts, which will affect the output of the agent's learning algorithm. So in this setting, it would be inappropriate to assume that ATW, that the agent's behavior is not going to depend, not going to vary as the principal's mechanism varies. However, implicit in standard definitions of regret is the idea that the state is not going to be, or I guess in this case, the actions would not be changing with respect to the principal's behavior. Because we have this somewhat different, and in our setting, I believe more appropriate definition of regret, standard no regret algorithms do not guarantee no regret for the principal. And in particular, there are no algorithms that can guarantee no regret for the principal without making, if we don't make any assumptions on the agent's learning algorithm or the outcomes obtained by the agent's learning algorithm. However, we can design a mechanism that works well under for agents that are counterfactually calibrated. So in our running example, our mechanism is very simple. It's 3 steps. First, we fix the tuning parameter to epsilon, but we think of it as going to 0 as the number of tasks goes to infinity. Second, we form a calibrated probabilistic forecast, PT, of the difficulty of the present task, right? There are standard algorithms that can do this. And finally, we're going to set a contract for task T that is very similar to the common prior contract, right? The difference being that instead of the common prior P, right, we are going to substitute P with the forecast PT. We're also going to bump up the agent's incentives for working by something that is proportional to epsilon. So that's our mechanism, very simple. And we're going to see that, okay, we can derive regret bounds for this mechanism. So I'm going to show you 2 results. Okay, the first result is somewhat more general, so weaker assumptions. The second result is going to give us vanishing regret as opposed to just bounded regret. Both theorems I'm going to state asymptotically, but so in the limit as the number of tasks goes to infinity. But in the paper, we do deal with the finite sample case. So our main assumption is going to be that the agent's algorithm is counterfactually calibrated on the realized history. Now, I haven't actually told you what counterfactual calibration means yet. And we're going to be doing that in a bit. So first, we're going to see what it buys us, and then we're going to go into the detail and try to motivate and define it. Our result here is that the principal's regret in the limit is at most C, the cost of effort for the agent, times 1 minus P hat, which is the empirical frequency of hard tasks. Why does this arise? Well, we go into more detail in the paper, right? And in particular, we see how this generalizes beyond our own example. But what you should think is that this is the price of ignorance, the price of our ignorance about the agent's information, right? If the agent is more informed than us potentially, but we do not know how much more informed the agent is, we are not going to be able to guarantee no regret. Of course, we can always consider settings where the agent is not more informed than us. And that's precisely what we're going to do in our next result. So we're going to maintain the assumption that the agent is counterfactually calibrated. And we're going to add the assumption that the agent is not better informed than we are, which we can formalize as saying that the agent has non-negative regret on the realized history. In that setting, we can argue that the principal's regret actually vanishes on our mechanism. So having achieved our objective of no regret mechanism design for the principal, let's now turn to the agent's problem and sort of try to understand why counterfactual calibration is necessary and sort of what does it actually mean. So first, we're going to sort of observe that some kind of behavioral assumption is needed to bound the principal's regret. But no regret assumptions for the agent are not enough. Now, the issue here is that the agent might appear to be informed. And what do we mean by that? We mean really that the adversary, right, who is in this problem is who's choosing both the learning algorithm of the agent and the sequence of difficulties. The adversary can correlate the actions and the difficulties to make it appear as if the agent has additional information. This kind of information makes no regret assumptions inadequate for our setting. To see all of this more carefully, we're going to turn to a counterexample. Okay, so our goal here is to exhibit an algorithm for the agent that obtains no regret, but for which the principal's problem is infeasible, for which you cannot sort of get a reasonable regret bound for the principal. So here's the algorithm. So first it's going to basically have an on-off switch to determine whether or not to use information. So this algorithm is very well informed somehow, but can decide to sort of forget that information based on the actions of the principal. And specifically, what we're going to condition on is the wage specified by the principal following success in the first period. Okay? So if that wage in the first period is odd, then the agent will play the best in hindsight action, which we might as well suppose is to work. Okay, so here each box is going to represent a task. The color is going to be green if the agent works. It will be pink if the agent shirks. And E will indicate that the task is easy. H will indicate that the task is hard, right? We see here that the sequence of tasks is alternating between easy and hard. Okay, so if the wage in the first period is odd, the agent will do something that is uninformed, sort of not particularly well informed, but still rational and pretty good, best in hindsight. On the other hand, if the wage in the first period is even, then the agent will alternate. So the agent will actually sort of anticipate the state correctly, the difficulty correctly, and work in the easy periods and shirk in the hard periods. Now the principal prefers the second case, right? And the reason for that is essentially that the principal needs to compensate the agent in general for the risk of working on a hard task, right? And if the agent is able to distinguish between the easy and hard tasks, there's no need to provide that additional compensation, and the principal can just compensate the agent for the cost of working, right? So it's actually to the principal's benefit that the agent is more informed. So what the principal wants to do here is to set the wage in the first period to be even, and then to choose some reasonably good mechanism. So that's fine. So the principal, as long as the principal here knows the agent's algorithm, he can guarantee no regret. But we can generalize this example so that the principal actually cannot guarantee no regret. Okay. So far what's on the slide is the exact same as what was on the previous slide. But now we're going to say, okay, before we had the sequence of alternating tasks, task difficulties beginning with an easy task. Well, suppose it maybe begins with a hard task. What we're going to do is have the agent's algorithm basically reverse its behavior if the first task is hard, right? So if the wage after the first period is odd, then the agent will pretend to be or act as if she is informed, alternating between working and shirking. And if the wage in the first period is even, then the agent will play the best in hindsight action, sort of the quote unquote uninformed action. All right. So now we see that basically, depending on whether the task, the task in the first period is easy or hard, the principal wants to choose the wage in the first period differently, right? Either even when the first task is easy, or odd when the first task is hard. But since the principal does not know the difficulty of the first task at the time that he is making the wage decision, there's no way to guarantee that the principal is going to choose correctly. And after having chosen possibly incorrectly in the first period, there's no way to recover from this mistake because the effects on the agent's algorithm are permanent. Okay, so this is an example of sort of like the frivolous behavior that we might see because our no regret condition is sort of too weak. And at the beginning, we said, okay, well, we want to strengthen the no regret condition to say no regret conditioned on the agent's information. Here we see that the agent has quite a bit of information. But of course, we haven't told you formally what is information, right? It's really just an artifact of the adversary sort of trying to frustrate the principal. Now, the key insight here is going to be that the information of the agent is in some sense revealed by her behavior on and off path. So we can take an example similar to what we just discussed, and we can say, okay, suppose that the agent's actions under our mechanism are just to always work, right? So the uninformed, but still, rational thing. And her actions under the fixed contract are this sort of hyper-informed behavior where she can distinguish between easy and hard tasks. What we notice is that the pair of actions of the agent under our mechanism and under the fixed contract is going to pick up on any information that is sort of revealed either through her behavior under our mechanism or through her behavior under the fixed contract. And in this case, the pair is going to be able to distinguish between the easy tasks and the hard tasks perfectly because the agent reveals her ability to do so if we play the fixed contract W. So this brings us to counterfactual calibration, right? The idea is that the agent must exploit her revealed information. Information here is going to be defined by the agent's actions on and off path. Specifically, IT is going to be the vector consisting of the contract WT for task T, which is observed, the action AT under the mechanism that the principal has, and the counterfactual actions AWT under each of the fixed contracts that the principal could have played. Again, fixed contract being we play the same contract from beginning to end without regard for the history. Counterfactual calibration simply says that we want to impose no contextual ret where the information IT is the context. Hopefully that's clear enough. More formally, counterfactual calibration we can write down as no counterfactual internal ret, right, which is a refinement of internal ret as follows. But of course, we go into more detail in the paper. Okay, so to conclude, we replace the common prior assumption in a rich class of single agent mechanism design problems with online learning. We introduce counterfactual calibration, which we can think about as a non-Bayesian notion of rationality that does not rely on distributional assumptions. Basically, it said that if the agent reveals useful information on one path, she must also exploit it on other paths. And finally, we think that this work raises a number of interesting open problems, such as, for example, the extension to bandit feedback, as opposed to observing the state in every period. Mechanisms that learn about the agent's information in order to sort of tighten our regret bounds when the agent is potentially informed. And of course, sort of computational tractability in a number of dimensions. Thanks very much.